we shall going to start module 2 of chapter 8. In this module, we shall discuss the applications of Euler-Lagrange equation. Calculus of variations, which is a pillar of classical mechanics, is used to optimize some definite integrals. It has wider applications in finding trajectories and geodesics. It can be used in maximizing the lift of aeroplane wings, maximizing the strength of a pillar or beam or arc. It can be used in minimizing the air resistance on a bicycle helmet and many others. Now we shall discuss the different applications of Euler-Lagrange equations. In this module, we shall apply Euler-Lagrange equation in finding the extremal for different physical problems. Problem 1. Show that the shortest curve between 2 points in a plane is a straight line. The length of an arc in a plane is given by ds is equal to square root of dx square plus dy square. The total length of any curve passing through the points x1 y1 and x2 y2 is given by capital I equal to integration x1 to x2 ds. If we put the value of ds, then we get integration over x1 to x2 square root of dx square plus dy square. After dividing by dx square, we get the result which has been written in the right hand side. Here S is the arc length, please note it. Since we have to find a shortest curve, so I must be minimum. The necessary condition for this is del del y of f minus ddx of first order partial derivative of f with respect to y dash equal to 0. This is nothing but the Euler-Lagrange equation. Here f is given by this, that is square root of 1 plus y dash square, which is a function of y dash. So, f becomes function of y dash. Here y dash stands for ddx operated on y. Since f depends on only y dash, so we have del del y of f equal to 0, whereas del del y dash of f gives this. If we substitute these two in the Euler-Lagrange equation, we get this one. After integration, this gives y dash divided by root over 1 plus y dash square equal to constant. From this, we have y dash square equal to c square into 1 plus y dash square. We get it after squaring. After simplification, this gives this one. As c is constant, so square root of 1 minus c square is also constant. So, we can write it as another constant which is a. This on integration gives y equal to a into x plus b. A and b being constants, this equation represents a straight line. Now, consider problem 2, which is a famous problem known as Brachistochrone problem. Find a curve y equal to y function of x in the vertical plane passing through the origin and the point capital P1, whose coordinate is x1 y1, such that a particle starting from rest at O and sliding down the curve without friction will reach the end of the curve in a minimum time. This is the physical sketch of the problem. This is the curve. Here is the point P1, x1, y1. The curve starts from this and passes through this point. P is a general point whose coordinate are given by x, y. This is x and this is y. The curve is sliding down this path in this way. We have to find a curve so that the particle reaches at the end point in a minimum time. We shall find the shape of the curve. By the principle of energy, we have kinetic energy is half into mass m into velocity square, that is half mv square, is equal to potential energy which is given by this, that is mass m into g into x, where g is the acceleration due to gravity, x is the displacement. From this we get v equal to square root of 2 gx. Here we have taken the positive sign since we are considering the velocity. B can be written as d dt of s, where s is the arc length. Therefore, d dt of s equal to root over 2 g into x. This can be written in this way. If we write this as this, then we get into dx. Since d dx of s is given by this one, we replace this portion by this and get this result. Now, integrating this relation, we get t. Please note that we are integrating from 0 to t. This corresponds x equal to 0 to x1. At t equal to 0, the particle is at the origin, so x equal to 0. At t equal to t, the particle reaches at the end point, that is P1 point, so it becomes x1. So, t equal to integration 0 to t dt equal to 1 divided by root over 2 into g, integration x equal to 0 to x1 square root of 1 plus y dash square divided by root over x into dx. For minimum t, from Euler-Lagrange equation we have this relation. This is a necessary condition, that is del del y of f minus d dx of first order partial derivative of f with respect to y dash equal to 0. Y dash means d dx of y. Here f is a function of small x and y dash. Please note that f is independent of y. So, we can use the special case of Euler-Lagrange equation, that is we have this one, that is first order partial derivative of f with respect to y dash equal to constant. After calculating this partial derivative, we get this one. So, this gives constant. If we choose constant c and square this result, we get this relation. If we put again small a equal to 1 divided by 4gc square, which is again a constant, then we can put the result in this form. On simplification, this becomes this. Next, we substitute x equal to a into 1 minus cos theta, a is a constant, in the above expression. Then we get y dash equal to this one, divided by this one. On simplification, this becomes this. Using the formulae for this and this, on simplification this becomes tan of theta by 2. Now, y dash, that is ddx of y, can be written as dd theta of y into ddx of theta equal to tan theta by 2. Since dd theta of x equal to a sin theta, since x has been given here, we just calculate the ordinary derivative of x with respect to theta and get it. So, dd theta of y is given by this. On simplification, this gives this one. This can be written as this one with a formula. If we integrate the result, then we get y equal to a into theta minus sin theta plus integrating constant. Now, we want to find this value of this integrating constant. At the origin, that is at x equal to 0, y equal to 0, there theta is also 0. So, the constant of integration vanishes. Using this value, here we get constant of integration vanishes. Thus, we get y equal to a into theta minus sin theta and x equal to a into 1 minus cos theta, which are the parametric equations of a cycloid. Theta is the parameter here. Please note that the word brachistochrone means shortest, whereas chronos means time. Calculus of variations deals with the optimization of a functional. Using this, we can obtain the trajectory and geodesics of classical mechanics. We have already defined about trajectory in the previous chapter. Now, we shall define the geodesic. Geodesic on a surface is nothing but a curve along which the distance between 2 points on that surface is minimum. Now, we shall use Euler-Lagrange equation to solve some problems related to geodesics in this module. Next, we consider third problem. Find the geodesics on a sphere of radius a. Let us define geodesic. A geodesic on a surface is a curve on the surface along which the distance between any 2 points of the surface is a minimum. In spherical polar coordinates r, theta and phi, we have ds square equal to dr square plus small r into d theta square plus small r sin theta into d phi its square. Since for a sphere of radius a, we have small r equal to a, therefore, dr equal to 0. Using this, we get ds square equal to a square into d theta square plus a square sin square theta into d phi square. Therefore, if we consider dd theta of s, its square is given by a square plus a square sin square dd theta of phi its square. Integrating this relation with respect to theta between theta 1 and theta 2, we get s equal to integration theta 1 to theta 2 a into root over 1 plus sin square theta to dd theta of phi its square d theta. Thus, f becomes f equal to a into square root of a plus sin square theta into dd theta of phi its square. This is independent of phi. So, Euler-Lagrange equation reduces to del del phi dash of f equal to constant. Please note that phi dash is dd theta of phi, that is this one is the phi dash. Therefore, using this relation we have, after calculating the partial derivative, this one, we get this result. Squaring this, we get this result. Taking the square root, we get the value of phi dash, which is given by this. If we integrate this, we get phi is a function of theta equal to integration k cosec square theta into d theta divided by root over 1 minus k square minus k cot theta its square plus integrating constant C2, as it is an indefinite integral. This on integration gives cos inverse k cot theta divided by root over 1 minus k square plus C2. Rewriting this, we get cos of phi minus C2 equal to cos phi into cos C2 plus sin phi into sin C2. So, we have cot theta equal to, if we multiply this, we get cot theta equal to root over 1 minus k square divided by k into cos of phi minus C2, which has been written in this way. So, in this expression we are multiplying by square root of 1 minus k square divided by k and get this result, where capital A is given by this one, this is a constant, whereas capital B is given by this one, this is another constant. So, we get the equation as given by equation 1. If we multiply equation 1 by a sin theta, we have a cos theta equal to capital A into small a sin theta into cos phi plus capital B into small a sin theta into sin phi. This can be written as z equal to capital A into x plus capital B into y, where x is given by this one, y is given by this one, z is given by this one. Please note that r equal to a is on the surface of the sphere. Thus, we obtain a plane. This is an equation of a plane passing through the origin, which is nothing but the center of the sphere, which cuts the sphere along a great circle, which is the geodesic on the sphere. Consider another problem. Determine the equation of the geodesics on a right circular cylinder of radius a. In cylindrical coordinates small r, theta and z, we have this relation, that is ds square equal to dr square plus r into d theta square plus dz square. This can be written in this way. Please note that since the radius is given by small r equal to a, so dr vanishes, thus we get this result. Taking square root, we get this one. We have this result. This is the functional. Please note that this is independent of z. Thus, by Euler-Lagrange equation, we have this one. Calculating the partial derivative, we get this. After squaring, we get this one. Here z dash means dd theta of z, which is the ordinary derivative of z with respect to theta. Taking square root of this, we get this result. As k into a divided by root over 1 minus k square is a constant, we put it as k star. On integration, this gives z equal to k star theta plus c1. c1 is a constant of integration. Thus, we finally have small r equal to a, z equal to k star into theta plus c1, which is a circular helix. c1 is a constant, please note it. Minimum surface of revolution problem. Find a curve y equal to y function of x joining 2 points capital A whose coordinates are x0, y0 and capital B coordinates are x1, y1 such that when it is rotated about the x axis, it generates a surface of minimum area. Consider this figure. This is the curve y equal to y function of x, P is a point on it. Here is the point A whose coordinates have been given, B its coordinates are also given. If we rotate this surface about this axis, we get such type of surface of revolution, which has been shown in figure 8.3. Now, let us calculate the surface area. Surface area is given by S equal to, we have to integrate between capital A to capital B, 2 pi into y ds. From the formula of area, we get it. If we put the value of ds, we get this one. Y dash means ddx of y. Therefore, here the functional f becomes 2 pi into y, 2 pi into y into root over 1 plus y dash square, this one, which is a function of y and y dash. Now, we have to optimize it. Euler-Lagrange equation gives small f minus y dash into f of y dash. Here y dash is at the suffix, which means partial derivative of f with respect to y dash equal to constant. After calculating this partial derivative, that is del y dash of f, we get this result. F has been just substituted, which gives constant. On simplification, this gives this one. Taking square, we get this result. If we put y dash equal to sin hyperbolic t, then y square becomes this one, which gives a square cos hyperbolic square t. Therefore, y equal to a cos hyperbolic t. So, ddx of y is sin hyperbolic t, which can be written in this way. If we put the value of dy, it is the differential of y in this way, then we get dx equal to a dt, which on integration gives x equal to a into t plus b, b is the integrating constant. Eliminate t between x and y, we get this result, which is nothing but a catenary. and this equation and these equations are the parametric equations of the curve. Calculus of variations has its origin in the generalization of extremization. Basically, it deals with the optimization of definite integrals. It has wider applications. In this module, we have discussed some important applications by using Euler-Lagrange equations and its special forms.